Welcome to Maths with EJD once again. Today, still talking about matrices, we'll be looking at the Cayley-Hamilton theorem, which is one of the important theorems when you talk about matrices, right? It's a very interesting theorem, very simple too. The Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. Okay, of course. The idea of characteristic equation um, is it will probably be new to you, but of course you know what square matrix is, right? And once you understand what characteristic equation is, then it means that then you get the gist. But definitely, if you say that something satisfies an equation, for instance, if you have x squared plus 4x plus 4 equals 0, right? X squared plus 4x plus 4 equals 0. By the time you solve this, you're going to get minus 2 twice. So that means minus 2 satisfies this equation. That means if you put minus 2 into this equation, you get 0. That is what it means for minus 2 to satisfy that equation. So it means that for every square matrix to satisfy its characteristic equation, it means that if you put a square matrix into its characteristic equation, you get 0. And that's what you have on the second line. That in other words, if A is an n by n matrix, that's a square matrix for sure, and P of lambda is its characteristic polynomial. Of course, when you equate a polynomial to 0, it becomes an equation. So if A is an n by n matrix and P of lambda is its characteristic polynomial, then substituting A for lambda in P of A results in the 0 matrix. So there's a P of lambda, then later you put A for lambda so that it becomes P of A, and that results in the 0 matrix. So if you do that and you get 0, that means you have proven the Cayley-Hamilton theorem for a square matrix. Then this theorem can be used to find a given power of a matrix as well as the inverse of a non-singular matrix. So you can find the inverse of a matrix using the Cayley-Hamilton theorem. You can also find maybe if the matrix is A, right? You can find higher powers of A, like A raised to power 5, A raised to power 7, A raised to power anything for the matrix based on the Cayley-Hamilton theorem. Okay, so let's see our first example. It's a 2 by 2 matrix. You want to show that A is 3, 2 minus 1, 4 satisfies the Cayley-Hamilton theorem. We already know that once it is a square matrix, it has to satisfy the Cayley-Hamilton theorem. And then since you also know that it can find higher powers of the matrix, then here the question is also going further to ask you to find A raised to power 3, So the solution, the first thing you want to do from what we saw in the definition already, we need to check the characteristic polynomial of the matrix. And it is given by pi of lambda. Now, this is the definition now. The definition is pi of lambda equals the determinant of A minus lambda I. Lambda is a scalar value multiplied by the unit matrix, So this is the definition of the characteristic polynomial with respect to whatever matrix you might be considering. Okay, so now that you have your matrix to be 3, 2 minus 1, 4, the matrix is 3, 2 minus 1, 4. So that's what you have here, minus lambda I. That's lambda into 1, 0, 0, 1 for a 2 by 2 matrix. If it is 3 by 3, it goes to 1, 0, 0, 0, 1, 0, 0, 0, 1. So you have, this is lambda I, this is A. Then if you go ahead, you can have rho of lambda, not P. This is rho. It's a Greek alphabet, a Greek letter rather. So rho of lambda, and that is equal to 3 minus lambda, 3 minus lambda, 2 minus 0, 2, minus 1 minus 0, minus 1, 4 minus lambda, 4 minus lambda. So that's why you have this. So this is basically the expression for the characteristic polynomial. Now, this polynomial becomes an equation if you just say this is equal to 0, then it becomes an equation. When we get to talk about eigenvalues and eigenvectors, you will relate a lot with the idea of with the polynomial characteristic equations. But for now, let's focus on the characteristic polynomial. Okay, so you have this, and of course, determinant means that you already know the procedures for looking for determinant. So this is a 2 by 2 matrix, and you have to get the determinant here, right? You have 3 minus lambda into 4 minus lambda minus 2 times minus 1. So that's what you have here. You have 3 minus lambda multiplied by 4 minus lambda minus 2 times minus 1. So then you expand all this now, and you have 3 times 4, 12. 3 times minus lambda, that's minus 3 lambda, minus lambda times 4, that's minus 4 lambda, minus lambda times minus lambda, that's lambda squared. Minus times minus is plus, 2 times 1 is 2. So that is tidied up, and then you can go ahead to express that, to simplify that, right? So you have lambda squared coming out here, minus 3 lambda minus 4 lambda is minus 7 lambda. 12 plus 2 is 14. So it means that the characteristic polynomial for this matrix would be P of lambda equals lambda squared minus 7 lambda plus 14. And the characteristic equation will be lambda squared minus 7 lambda plus 14 equals 0. Equals 0. So this is the characteristic polynomial. This is the characteristic equation. So for now, characteristic polynomial is all we need. And the next thing is, now that you have obtained the characteristic polynomial, to prove the Cayley-Hamilton theorem, it says that if you now replace the lambda here with the matrix you're working on, then it evaluates to 0. So if you substitute matrix A for lambda, that means instead of P of lambda, which is lambda squared minus 7 lambda plus 14, then you have, row of lambda. I keep calling that P. It's row of lambda, which is equal to lambda squared minus 7 lambda plus 14. So this becomes row of A equals row of A, which is equal to A squared. It's equal to A squared minus 7a plus 14i. Now, this becomes 14i because you're dealing with a matrix now. Here you're dealing with just regular numbers. But once you introduce a into it, this automatically becomes, so this is matrix A squared, 7 times matrix A, and this is 14. 14 cannot just stand on its own. So it has to be 14 multiplied by the unit matrix for 2 by 2. So that everything can be matrix together like that. Okay, so now that you have this, you want to establish that the matrix actually satisfies its own characteristic polynomial. So that, and to do that, you have put the A now. So bring the matrix. The matrix A originally, don't forget, is 3, 2, minus 1, 4. 3, 2, minus 1, 4. So row of A equals A squared minus 7a plus 14i means you have row of A, this is A squared minus 7a plus 14i, like that. And then you already know how to expand this. So you have 3, 2, minus 1, 4, 3, 2, minus 1 because it is squared. And then, of course, you have minus 7 into all that. So the next thing is you have, because this is in 2 rows, you have 3 minus 1 twice, and you have 2, 4 twice. Then you come back and invert 3, 2. We've done this a couple of times. So 3, 2 also on the first row, minus 1, 4. On the second row, then you multiply and add. So 3 times 3 is 9. Minus 1 times 2 is minus 2. 9 times 2. 9 minus 2 rather is 7. Then minus 3 minus 4, that's minus 7. 2 times 3, 6. 4 times 2, 8. That's 6 plus 8 is 14. Minus 2 times minus 1 is minus 2. 4 times 4 is 16. 16 minus 2 is 14. So you have A squared to be 714 minus 714. And then 7 times A is 7 times 3, 21. 7 times 2, 14. 7 times minus 1, minus 7. 7 times 4, 28. And then 14 into 1001 is 140014. Okay, so don't forget, we are going to establish that row of A will give us 0, right? So, of course, since you have all of these things, you have, so you can just say this is 7 minus 21 plus 14. 7 minus 21 plus 14. And that is 7 minus 21 is minus 14 plus 14, 0. Then next is 14. There's minus here. 14 minus 14, that's 0, plus 0, that's 0 here. Then minus 7, minus times minus is plus. So minus 7 plus 7, that's 0, plus 0. This also goes. Then 14 plus 7, 14 plus 7. Sorry, 14 minus 28 plus 14. Same location everywhere. So you have 14 minus 28 plus 14. So doing that 10 by 10, you have all this. And at the end of the day, everything just goes to 0. So by doing this, it means you have established the Cayley-Hamilton theorem that every square matrix satisfies its own characteristic polynomial, meaning that if you substitute a square matrix into its characteristic polynomial, it evaluates to 0, like you have here. So rho of A is 0 such that the matrix A satisfies the Cayley-Hamilton theorem. Now, don't forget the second part of the question is to find A raised to power 3. Normally to find A raised to power 3, you just need to do 3 2 minus 1, 4 raised to power 3, and you do that 3 times. But then with Cayley-Hamilton's theorem, you can just, get A raised to power 3 by not multiplying outrightly like that. I know adding things up might be a bit easier than multiplying them, right? So to find A cube, right, you've already seen that rho of A, from what we have established already, you have seen that rho of A is A squared minus 7A plus 49 is equal to 0. At least that has been established at the top here. So if that is the case, you can make, we are looking for A cube, right? And to get, there's no A cube in this expression, but there's A squared. So since you're looking for A cube, you can make A squared the subject of formula. And after making A squared the subject of formula, all you just need to do is to multiply through by A. If you multiply through by A, so you have A squared times A, that's A cube. 7A times A, 7A squared. 14I times A is 14A. 14I is like 14 times 1. So it's more like just 14 multiplied by A. So you have 14A. So instead of having to expand the normal A 3 times, you can express A cube as 7A squared minus 14A. And we already got A squared previously, so you just need to bring it down. So you see that A cube is 7A squared minus 14A. So A cube equals 7 times A squared. You remember we got this before, that 714 minus 714. Minus 14 into 3, 2 minus 1, for that's the original A. So all we just need to do now is to multiply out and add up. 7 times 7, 49. 7 times 14 is 98. 7 times minus 7 minus 49. 7 times 14 again, 98. Then you have minus 14 times 3 is 42. 14 times 2, 28. 14 times minus 1 minus 14. 14 times 4 is 56. So then you just subtract 10 by 10 because you have negative in between. 49 minus 42, that's 7. 98 minus 28, that's 70. 40 minus 49 plus minus 49 minus minus 14, that's minus 49 plus 14, that's minus 35. Then 98 minus 56, that is 42. Then, of course, we see that 7 is common everywhere. You can actually leave it this way, right? But since 7 is common everywhere, you can bring out the 7. So you have 7 into 1, 10, minus 5, 6. So that is A raised to power 3 without having to keep multiplying A. So that's a case of 2 by 2. Let's use a 3 by 3 example and see how that works. So we have a very simple matrix here to deal with. You want to show that B equals 1, 2, 2, 2, 1, 2, 2, 2, 1 satisfies the Cayley-Hamilton theorem. Hence, you're looking for A raised to power 4. Mind you, if you do a 2 by 2 matrix, the highest you're going to get is A squared. If you do a 3 by 3 matrix, the highest you're going to get is A cube. So you can always multiply by A to get A raised to power 4. So I can even ask you to find A raised to power 5. You just do A raised to power 4, or you can just multiply by A squared. So you get A raised to power 5, and then you get the other part and, just, bring in the matrices and solve to get A raised to power 5, if that's what you're looking for. Here we are looking for A raised to power 4. So here, the first thing you want to do when it comes to Cayley-Hamilton is to find the characteristic polynomial. And since you are dealing with matrix B now, so rho of alpha is B minus lambda I. So since it is B minus lambda I, you already know the B is 1, 2, 2, 2, 1, 2, 2, 2, 1. But then by the time you do minus lambda I, from what we did the other time, you already know that all the lambdas will be coming to the numbers along the main diagonal. So you have 1 minus lambda, 1 minus lambda, 1 minus lambda. Every other number remains just the way it should be. And since this thing is determinant, right? You already know how to find determinant. You pick, of course, you assign the necessary signs, plus, minus, plus, right? Like you already know. So here you have plus 1 minus lambda, cross this, you have minus 1 minus lambda, 2, 1 minus lambda. Then the next thing is you take minus 2, you know, this minus 2, that is what comes here. And then cross this column, cross this row. So you have 2, 2, 2, 1 minus lambda, like that. And then lastly, you take plus 2, this plus 2, it comes here, and then cross its row and its column. So you have 2, 1 minus lambda, 2, 2 coming right here. So the next thing you just have to do is to simplify. So you get to simplify this. So you see 1 minus lambda is out here. So this times this, that's 1 minus lambda squared, minus 2 times 2, that's 2 squared. Then minus 2 here, this is it. Then you have 2 into 1 minus lambda, minus 2 times 2, that's 2 squared, plus 2 here. Then 2 times 2 is 2 squared again, minus 2 into 1 minus lambda. So we go ahead to tidy up again. So this is 1 minus lambda is here, but this is 1 minus lambda squared. So there's this rule that a minus b squared is equal to, a minus b squared is equal to, a squared, this a squared, minus 2 times a times b plus b squared, whenever you have this. So that's a squared minus 2ab plus b squared. So if you are doing the same for minus lambda squared, that's like 1 squared minus 2 times 1 times lambda, that's minus 2 lambda, then plus lambda squared, like that. That's why you have 1 minus 2 lambda, 1 minus 2 lambda plus lambda squared. Then, of course, minus 2 squared is minus 4. Then you have minus 2 here. 2 times 1 is 2. 2 times minus lambda, minus 2 lambda. Then minus 2 squared, that's minus 4. Then plus 2 here. 2 raised by 2 is 4. Then minus 2 times 1, that's minus 2. Minus 2 times minus lambda, that's plus 2 lambda. So that's also simplified. Okay, so we keep simplifying. Next step is to tidy things up. So we now have row of lambda is 1 minus lambda into 1 minus, okay, now we have lambda squared is coming here, then minus 2 lambda is here. So 1 minus 4, that's minus 3. You have 1, you owe 4, so you still owe 3, and then you have minus 2. Minus 2 is here. Then 2 times minus 4, that's minus 2. Then minus 2 lambda, that's it here. Then plus 2 is here. So 4 minus 2 is 2. Then you have 2 lambda, like that. So we still are tidying things up. So we can expand now. So 1 times lambda squared, that's lambda squared. 1 times minus 2 lambda, that's minus 2 lambda. 1 times minus 3, that's minus 3. And then you go on again to minus lambda times lambda squared, that's minus lambda cube. Minus lambda times minus 2 lambda, that's 2 lambda squared. Minus lambda times minus 3, that's plus 3 lambda. Then minus 2 times minus 2 lambda, that's 4 lambda. Minus 2 times minus 2, that's plus 4. 2 times 2, 4. 2 times 2 lambda, 4 lambda. Okay? Things can get really, it can become a lot, so you have to be careful and calm in doing this. So at this stage, we just want to aggregate similar terms. So, and what are the similar terms there? We have minus lambda cube, so that comes first. There's no other lambda cube, so that comes. And then the next thing is the lambda squares. So you have lambda square here, you have 2 lambda squared. That's everything together is 3 lambda squared. And then you have the lambdas. So minus 2 lambda plus 3 lambda, that's 1 lambda, plus 4 lambda, that's 5 lambda, plus 4 lambda, that is 9 lambda. So you have to be careful that you pick everything necessary. Then talking about the constants now, you have minus 3 plus 4, that's 1, plus 4, that's 5. So at the end of the day, the whole thing is tidied up. Your row alpha is tidied up to be minus lambda cube plus 3 lambda squared plus 9 lambda plus 5. So this is what you call the characteristic polynomial now. This is the tidied up characteristic polynomial, which you can now use for anything you want to do next. So this is the characteristic polynomial. So we know that to prove the Cayley-Hamilton theorem, we substitute A for lambda in the characteristic polynomial. So if rho of lambda is this, then rho of A is going to be this, minus lambda cubed, that's minus A squared, A cubed, plus 3 lambda squared, that's plus 3A squared, plus 9 lambda, that's 9A, plus 5, which is just a constant. So that'll be 5I because you're now dealing with matrices. So that's the way to make sure everything is a matrix. So the next thing is to put the matrix. You remember the original matrix is 1, 2, 2, 2, 1, 2, 2, 2, 1. So this is minus A cubed. So I have minus A cubed plus 3A squared, that's 3A squared, plus 9A plus 5, the unit matrix in 3 by 3, that's 1, 0, 0, 0, 1, 0, 0, 0, 1. So because you already know how to multiply, by the time you multiply this out, you know, of course, one thing you can do is if you have to show all the steps, you can do this first and you get this, and then you now multiply this again by this, then you get this. So, but you already know the steps. That's why I'm jumping this in this case. We've done multiplication a couple of times. So the cube of this is actually 41, 42, 42, 42, 41, 42, 42, 42, 41, like that. Plus 3. The square of this is 9, 8, 8, 8, 9, 8, 8, 8, 9. Then, of course, every other thing goes like that. So there's minus outside there. So the minus applies to everything here. Then 3 times 9, 27, 3 times 8, 24, 3 times 8, 24, and that applies to the rest. Then 9 times all this, 9 times 1, 9, 9 times 2, 18, 9 times 2, 18. So that, then 5 times the unit matrix, you have all this. So now you have minus 41 plus 27, that's minus 14. All right. Is it minus 14? Yes. Minus 14 plus 9, that's minus 5. Minus 5 plus 5, this is 0 now. Then minus 42 plus 24, that's minus 18. Minus 18 plus 18, that is 0. Minus 42 plus 24, minus 18. Minus 18 plus 18, that's 0. Then everything, by the time you do 10 by 10 like that, this minus 42 plus 24 minus 18 plus 18, that's 0. So if you do that all the way, you see that everything evaluates to 0. That means that this 3 by 3 matrix again satisfies the Cayley-Hamilton theorem. Okay, now that that is settled, then you want to find A raised to power 4. You want to find A raised to power 4. You already know that rho of A is 0. At least that has been established up there. Even if you don't, but now that it is established, going forward, anywhere you go, you should always know that the characteristic polynomial of a square matrix, when you evaluate, when you substitute a square matrix into its characteristic polynomial, the answer is 0. So even if you don't prove it, that's established from what we have seen so far. Now we need A raised to power 4. So don't forget the row A originally is this minus A cubed plus 3A squared plus 9A plus 5. And that's what you need here now. So since you're looking for A raised to power 4, row A is 0. So that means that 0 will be equal to that row A we got, which is minus A cubed plus 3A squared, plus 3A squared plus 9A plus 5I, all this. So because you need A raised to power 4, and the closest thing to it is A cubed, so you can bring the A cubed out here. That's why you have it at the other side. So every other thing remains 3A squared plus 9A plus 5I. So since you need A raised to power 4, so you can multiply through by A. So that means A raised to power 3 times A, that's A raised to power 4. 3A squared times A, that's 3A raised to power 3. 9A times A, that's 9A squared. 5I times A, that's 5A. So it simply means that your A raised to power 4, A raised to power 4 now is equal to 3 times A cubed plus 9 times A squared, which we already got before, plus 5 times A, which is 1, 2, 2, 2, 1, 2, 2, 2, 1. So, and of course, like we already obtained before, A cubed, this is A cubed, we already got all this. So 3 times all this now, 3 times 41 is 123, 3 times 42 is 126, another 126 because it's 3 times 42 here. Then 9 times 9 is 81, 9 times 8, 72, 9 times 8, 72. Then everything goes on like that. Then 5 times 2, 5 times 1, 5, 5 times 2, 10. Just tidy up all that. And then the next thing is to add up all these terms. So 123 plus 81 plus 5, that is 209. 126 plus 72, that is 198 plus 10, that is 208. 126 plus 72 plus 10, another 208. So if you do all that, you get all these values right there. So that is your a raised to power 4. So that is the idea of the Cayley-Hamilton theorem. So every square matrix satisfies its own characteristic polynomial. And that means if you put a matrix into its characteristic polynomial, you get 0. And because you can get that, you can actually get higher ordered matrices from that. So that's why you have this exercise to try your hands on. Show that the following matrices satisfy the Cayley-Hamilton theorem. So you have T, you have U, and you have V. Then after showing that, to show that, find the characteristic polynomial. Once you have tidied up the characteristic polynomial, substitute these matrices and make sure they evaluate to 0. Once you evaluate to 0, that means the Cayley-Hamilton theorem is satisfied. And then you can now go ahead to find these higher orders. 2 by 2 will give you something power 2. So you can just multiply through by t and you get t cubed. This one will give you something power 3. So you get u raised to power 4 and you get v raised to power 5. If I can even add to it, that you should find like t, you can also find t raised to power 4, u raised to power 5, and v raised to power 4. You can also add that. So it means whatever t cube t raised to power 3 you got, just multiply by another t, and you move on like that to get all this. So with that, we've come to the end of this particular one. Thank you so much for listening. See you in the next video where we talk about how matrix inversion using the Cayley-Hamilton theorem. See you.